lesson. Okay, so now the recording button is on. So again, a very good morning to all of you, students of 4 Akid and 4 by Juri. So today we will have our lesson on 6.3 image formation by lenses. Okay. Um, so I hope this will be a two-way discussion. So along with the discussion, if you have anything to ask, you may just open your mic or you can type your answer in the in-call messages. Okay, so without further ado, let us begin 6.3 image formation by lenses. So this is the third topic on chapter 6. So for the first learning standard 6.3.1, so each of you need to know how to identify convex lens and concave lens as converging and diverging lenses respectively. Okay, so first and foremost, you must understand and get to know what is meant by lens. Alright, so there are two figures there, the first figure on top and the second figure below. Okay, so it say that the first figure is lens, okay, but the second figure is not lens. Can you tell me the difference between these two figures? What do you think make the first figure as a lens? Why do you think the second figure is not considered as lens? Any idea? Why the first figure is called lens? Why the second figure is not called as lens? Anyone would like to give a try? What is the difference between the first and the second diagram of the figure? Okay, so actually if you see, okay, so what is meant by lens? Okay, student, lens is a piece of transparent material. Transparent material mean we can see through. Okay, example, a glass, a perspex, plastics. Okay, second, it must have two surfaces where one of the surface must be curved shape, okay, or curved surface. So this is the definition for lens. It is a transparent material such as glass, perspex or plastic with two surfaces where one of the surface must be a curve. So if we go back to this figure, the first diagram, it has two faces. One is a plane surface, another one is a curved surface. So we call it as a lens. For the second figure, you can't see any curved surface there. Okay, so it is not considered as a lens. We cannot call it as lens because it does not have any curved surface. All right. Okay, so what happened? How does lens works, students? So generally, lens work based on the phenomenon called refraction of light. Okay, so when light passing through a lens, what happen? The light will be refract. Okay, it will refract due to the light travel into different medium of different optical density. Remember, we learned refraction of light in 6.1. When light travel through two medium of different of optical density, so the light will refracted. Okay, so this is how the lens work based on the phenomenon called a refraction of light. All right, and this slide tells you there are two types of lenses. Generally, we have two types of lenses. The first one is called as convex lens. You can find this in your textbook as well. Convex lens, also known as converging lens. Okay, for example, we have three examples there. The first one is called biconvex. Okay, both surface has a convex shape, mean it curve outwards. Okay, and then second, we have plano-convex. It has one curved surface. The other surface is a plane surface. Okay, then the third example is the convex concave, or it called as a meniscus. Okay, so all these three are example of convex lens. Convex lens are thicker at the center. Okay, you look at the structure, they are thicker at the center. Okay, second type, we have concave lens, or also known as diverging lens. Okay, example biconcave. This one is plano-concave, and third we have convexo-concave lens. So for concave lens, there are thinner at the center. So this is the first difference between convex and concave. Convex is thicker at the center while concave is thinner. Okay. Then this is the second characteristic you can see for both. So this is the ray diagram. What happened to the light ray that travel parallel to the principal axis to a convex lens. So what happened after passing through the optical center, they will be converged to a point. Converge means they all will be focused to a point F here. So that's why we call convex lens is a converging lens. Means the light ray will be refracted and focused to one point after passing through the lens. Okay, and this point F is called as a focal point, a point behind the lens. Okay, while for concave students, okay, we have parallel light travel here parallel to the principal axis. So what happened after it passed through the optical center, the light ray will be diverged. Okay, it will be refracted in the outwards direction. So we say the light ray diverge out, okay, from the lenses as it was diverged from the focal point in front of the lens. Okay, so that's why we call concave lens as a diverging lens. So if you look at these two diagrams, focal point for convex lens is behind the lens. So we call it as a real focal point. Okay, meanwhile, for concave lens, the focal point is in front of the lens. So we call this focal point as a virtual focal point, right? Okay, then. Okay, so that is the comparison between convex and concave lens. Okay, as for the beginning. Okay, now student in activity 1, this is one simple activity. I think we can conduct this by next week. Okay, to show convex lens as a converging lens and also to show concave lens as a diverging. So it's a very simple activity. So you just need a ray box with 3 slits. This is where the light ray coming from. So we have 3 slit rays. So there will be a 3 parallel light ray heading through the lens we place in front of here. Okay, so first we place a convex lens. So later you will see the light will be converge to a point after passing through this lens. And then when we replace this lens with the concave lens, you will see it will be diverge out. All right. Okay, so don't worry, we will try this next week. A very simple activity. So you can see how does concave diverge and how does convex lens converge a light. Okay, after passing through the. Okay, so this is all the instruction follow given from number 1 to number 8. So later you can read on your own. I also have shared the PowerPoint slide in your group. So you may check from there. Okay, so this is the observation we might see from activity 1. Okay, so you can see the GIF here. So what happened when we use concave lens, convex lens, see, it is focusing on a point. And for concave, it is diverged out after passing through lenses. So this is a few discussion we might consider. So the first question they ask, what happened to the 3 beams of light after passing through convex lens? So what happened? They will be converged, okay, at the focal point F behind the lens. While for concave, what happened to the light? It will be diverged, okay, from a focal point in front of the lens. All right, so are you clear until this point, student? Are you following me? Okay, so I might see some responses there. So anything you want to ask on the first 8 slides? Okay, are you doing good there, students? Okay, so I hope you're following me. So now let us continue with the second part. Okay, this is a table shows to you an important optical terms you have to know and understand very well if you want to do good for lens. All right. So the first one is optical center, student. Optical center given with the symbol O. So if you look at this diagram on the left side, okay, so this is the drawing for convex lens, and down here is the drawing for concave lens. So see the optical center there. This is the optical center for concave lens. So what is optical center, student? It is a point at the center of the lens, okay, where light rays passing through this point are not refracted. Okay, so if you look again at this diagram, the line at the center passing through the optical point continue travel in straight line, mean it does not refracted. Okay, second we have the principal axis. Okay, so principal axis is the center line which divide the lens in same portion, up and down in the same portion. Okay, above and below in a same portion. Okay, so principal axis is a straight line through the optical center of curvature for both surface. Okay, then the third terms we have the focal point. Okay, focal point here actually the symbol should be capital F. Okay, the focal point is F. So what is focal point? So this is the focal point for convex lens. It is behind the lens. Meanwhile, this is the focal point for concave lens. It is in front of the lens. So focal point for convex lens is a point where a light ray parallel to the principal axis converge at this point after passing through the lens. Okay. Meanwhile, the focal point for concave lens is a point where light ray that parallel to the principal axis appear to diverge, okay, from this point after passing through the lens. All right. Okay, then focal length. Okay, we have focal length there. You can see the focal length there for convex and focal length there for concave lens. Okay, sorry. So focal length given with the symbol small f. So what is focal length, student? It is a distance between the optical center and the focal point. So you measure the distance, it will give you the focal length. So this is the focal length for convex lens. Okay, so this is the focal length for concave lens. Okay, then we have object distance, okay, with the symbol U. So object distance is the distance between the object and the optical center. So we place an object in front of this lens. Okay, so you measure the distance of the object to the optical center, that will give you object distance. Okay, and then 6 we have image distance. So what is image distance? It is referred to the distance between the image and the optical center of the lens. Okay, so we will see this more detail when we come to the drawing of ray diagram for both convex and concave lenses. Okay, and last but not least is the axis of lens. So where the axis of lens, you can see it is a line that divided the lens into left and right equally. Alright, so straight line through the optical center which is perpendicular to the principal axis. So this is the lens axis for convex, the dashed line, and this is the lens axis for concave lens. Okay, so that is the first learning standard, to know convex and concave lens. Okay, together with the optical terms used in both structure. Alright. Okay, students, so our second learning standard is to estimate the focal length for convex lens using a distant object. Okay, how to predict or how to estimate the focal length of a lenses. Okay, for your information, each lens have their own focal length. Okay, it is depend on their thickness. Okay, depend on their power of the lenses. Okay, so this is the second activity. can be conducted to estimate focal length for convex lens. Okay, we may try this as well in school later on next week. Okay, so there are 4 steps involved. Very simple. So first, we prepare this apparatus, as you can see, a convex lens together with a holder, and then we need a long ruler, and then a white screen which is placed behind the lens. Okay, then this lens should be placed next to a window. Okay, so first our object will be a distant object yang jauh. Okay, but the object must be a static object, non-moving object. For example, it can be a tree, it can be a house, or anything which is immobile. Okay, so we direct the lenses to any distant object out from the window. Okay, then what happened? We will adjust the position of the white screen behind the lens until you can see a sharp image. Okay, until you can see a sharp image form on it. Okay, let's say we took this house as our object. So we directed our lens to this house. So we adjusted the position of the white screen until you can see a sharp image of house form in this white screen. Okay, so once we found that, we call the image form at the screen as a real image. Okay, later you will find there's a real image, there is a virtual image. So real image is an image which can be cast on a screen or which can be formed on a screen. Okay, then finally what we do, we measure the distance of the white screen to the distance of the optical center of the lens. So this will give us the focal length of this convex lens. So very simple. Okay, 4 steps involved to estimate the focal length of convex lens. All right. Okay, so this is the activity related to this estimating focal length for convex lens. Okay, sama juga, you need convex lens, mitero, lens holder, and widescreen. So later you may read the instruction as well. Okay, okay, students. Okay, that is the second activity, to estimate. Second learning standard, estimate focal length by using the four four ways. It's not from number 1 until number 4. Okay, then this is the third learning standard. Okay, the most important part in this chapter, okay, in this topic. Okay, to determine position and features or characteristic of image formed by convex and concave lenses. Okay, so how to know what kind of image will be produced when light ray passing through convex and concave lens. So there are a few rules of drawing the ray diagram we must apply. Okay, first, to know the position and characteristic of image formed by lenses, okay, student, we go for convex lens first. Okay, so if you look this slide, position and features mean characteristic. Okay, formed by convex lens, determined by drawing a ray diagram. Okay, and when we draw this ray diagram, there are 3 rules you must obey in constructing the ray diagram. So this one you have to listen very careful. Okay, listen carefully. So what is the first rule? Okay, so this is for convex and concave. So we apply the same rules for both lenses. Okay, number 1, you can see there is a light ray passing through the optical center in this direction for concave and convex. Okay, so both light ray are passing through the optical center. So what happened? The light ray will continue travel in a straight line without being refracted. Remember, any light ray passing through the optical center, it will be continued travel in a straight line, which means it is not refracted. Okay, so this is the first rule. So you can draw line from passing through optical center and continue travel in a straight line. Don't forget the arrow as well. Okay, so first rule, very simple. Okay, then we have second rule. Okay, the second rule for convex lens. Okay, see, for convex lens, there is a ray parallel to the principal axis. So see this light ray parallel to the principal axis. So this is our principal axis, the center line. Okay, so now this light ray is parallel. So after passing through the lens axis, so what happened? For convex lens, it will be converged to the focal point. Remember, convex lens is a converging lens. So the light ray will be converged to F. Okay. If you have a light ray down here also, let's say coming in this direction, parallel to the principal axis. So for this one, it will also, okay, converge to F. Sorry, the line I'm drawing is not straight. Okay, so I want to show you, it doesn't matter it is above or below the principal axis, as long as the light is parallel, it will be converged to point F. If the light ray passing exactly at the principal axis, so it will continue travel in a straight line. Okay, no refraction. Okay. Then for concave, what happened when a light ray parallel to the principal axis? So what happened? Remember, concave lens is a diverging lens. So it must be diverged out. So it will travel in this direction, and if you continue, it will be diverged from the focal point at the front. Okay, same here. If we have light ray coming from this direction, from below, okay, so what happened? It will be diverged out. Okay, and if you continue the dashed line here, it is started from the focal point at the front. Okay, so this is the second rules for drawing convex and concave lens. Drawing the ray diagram for convex and concave lens. And then the third rule, okay, the third rule, now our light ray is travel through the focal point. You see, this light ray travel through the focal point of convex lens. So what happened? After passing through, it will be refracted in a straight line. So actually, these rule 2 and 3 are opposite to one and another. Okay, just now travel parallel, then converge to F. This one passing through F and then refracted in a parallel direction. Okay, same goes to concave lens. Okay, now we have light ray here travel in this direction. Okay, so if you continue the line, it will be heading to the focal point. So what happened? It will be refracted in a straight line. Okay, so the third rule, any ray passing through the focal point will be refracted parallel to the principal axis. Okay, so later you will practice this. So to familiar yourself to these three rules of drawing. So later student, when we draw a ray diagram, in order to determine characteristic of image, you must use at least 2 out of 3 from this rule, okay, to find the intersecting point where the position of image form at. Okay, either you use the first and second rule, it can be the first and third rule, or you can use the second or third rule, depend on the position of the object given. Okay, later we will practice how to draw the ray diagram, okay, applying these 3 rules. Okay, then next. Okay, so this is the GIF, shows to you the example of image position and characteristic formed by convex lens. Okay, for convex lens, the characteristic and position of image is depend on the position of object which is placed in front of the convex lens. So later you will see there are 6, okay, 6 different positions where we can place the object in front of the convex lens. Okay, and here you can see when the object distance is varies, the image distance also varies. Okay, so this is the 2 possibility the position of image might form for convex lens. Okay, the image can be formed either at the same side at the object, which means at this side, okay, at the front, of the lenses, or the image can be formed behind, okay, behind the lenses, or it formed at the opposite side of the object. Okay, and the characteristic of image, it can be virtual or real. Okay, if the image formed at the same side of the object, we call the image as virtual image. Okay, you can see the black color is the object and the blue color arrow is the image. So form at same side, we call as a virtual image. If form at opposite side like this now, we call it as a real image. Okay, and then second characteristic, the image can be either upright or inverted. See now the image is upright. Okay, object above, image also above. Now this one inverted. Okay, object above but image form below. Okay, and then the third characteristic is about the size of the object. This one now show image is bigger than the object, so we call it as magnified. Okay, if the image form is smaller than the object, so we say the image is diminished. Okay, while when the size of image is equal to the size of object, so we call them as a same size. Okay, so this is another example of GIF, how to draw a ray diagram from the object parallel to the principal axis where it will be converged to the focal point behind lens. Alright, okay, so now this is the practicing on ray diagram for different object distance. Okay, so this is the first position. The object is at infinity. What does it mean? Object is now at infinity. Mean the object is at a very far distance. Okay, for example, a planet, okay, or a star, or a sun. We cannot estimate the exact distance, so we call U is at infinity. Object distance is at infinity. Okay, so the object is somewhere up here. Okay, so how to draw the ray diagram? Here we apply the first rule, the red color, the first rule. A light ray travel to the optical center. So it will continue travel in a straight line. Okay, then here we apply the third rule. Okay, apply the third rule. The light ray is travel through the focal point, and these two light must be parallel. Okay, so what happened? It will be refracted parallel to the principal axis. So you can see this is the intersecting point between these two line, red and green, where our image is formed at. Okay, you can see the image from there given by the purple arrow. It is formed exactly below F, below the focal point. Okay, so this will give us the characteristic of image. Okay, students, so how to memorize this? Very easy. Okay, this is the front part of the lens where normally we place our object here. So if the image form here, so the image will be virtual. If the image is formed behind the lens, mean at the opposite side, we call them as real. So for this one, we have real image. Okay, and somehow it is inverted. Okay, this is our image. Okay, it is inverted because we have our object up here very far away. A planet, a star, asteroid, very big in size. Okay, so the size is diminished, mean image is smaller compared to the object. So where do we apply this? We apply this in objective lens of a telescope. Okay, so telescope, we are used to observe a very distant object where the object distance is at infinity. Okay, okay, then this is the second position. So now you can see the object. The object is here. It is placed, okay, at a distance which is greater than 2f. So this is U. Okay, this is U, object distance. Okay, distance of object from the optical center. Alright. Okay, so here we apply the first rule. We draw a light ray from the object directed to the optical center, so it is not refracted. Continue travel in a straight line. Okay, and then we apply the second rule. Remember the second rule, we draw a light parallel to the principal axis and then it will converge at the focal point. So actually here you can also apply the third rule. Okay, but as I mentioned, enough to draw only two, only apply two. So if you use the third rule, so we draw a light ray from the object passing through F. So this one, it will be refracted in a straight line. So you will find they will meet at the same intersection point here. Okay, so this is where our image form at, in between F and 2F. Okay, the image distance. So what happened? The image form at the opposite side of the object. So we call it as real image. Okay, and then look at the position. Object is above the principal axis while image is formed below the principal axis. So we understand the image is inverted. And the size you can compare. Okay, you can see the object is larger. The image form is smaller. So we say the image is diminished. Diminished means dikecilkan. Okay, the image is smaller than the object. So we apply this in a lens of camera. Okay, students. Okay, and this is the third position. Okay, now we bring the object exactly at 2F. Okay, object distance equal to 2F. Again, where is the object distance? This is the object distance, U. Okay, distance between object and optical center. So here we apply the first rule, the red color line. Okay, light ray from the object passing through optical center, so no refraction. Continue travel in a straight. So this is rule number 1. Okay, and the green line is the rule number 2. Okay, we draw a light ray parallel to the principal axis and then it will converge at the focal point. So this is the intersecting point between these two lines. Okay, where our image form at exactly form below 2F. So again, it is real, inverted, and now the size is the same as the object. So we call they have the same size. Okay, so this one apply in a photocopying machine, right? Okay, then the fourth position. Okay, we bring the object closer. Okay, getting closer and closer to the lens. So now it is placed in between F and 2F. Okay, it can be anywhere. Does not necessary to be exactly at the center between F and 2. It can be closer to F or closer to 2F as long as it is between F and 2F. So again, we apply rule number 1, the red line, and then here we apply rule number 2, the green line. If you want to draw rule number 3, also no problem. You draw a light ray passing through the focal point, okay, and then here it will be refracted in a straight line. So they will meet at the same intersecting point here. Okay, so now our object, our image is real. Why real? Form at the opposite side with the object. Object is in front, image is behind, so it is real. Okay, and then inverted. Why inverted? Object is above, image form below. And the size you can compare. So now the image is larger compared to the object, so we call the image is magnified. Okay, so we apply this in objective lens of a microscope. See, we are using microscope to see a very tiny object. In the end, we will see the image has been multiplied for 1,000 times bigger compared to the actual object. Okay. Okay, then let's go to the next distance, the fourth and fifth distance. Okay, now U is at 2F. Okay, U is at 2F. So here, rule number 1 is applicable. Rule number 2 is also applicable. But rule number 3 is not applicable because the object is now exactly at F. So we apply rule number 1 and rule number 2. For this one, you will see these two lines are parallel. Mean there is no way they are going to intersect either at this side or at the opposite side. So what happened here, we say where is the image now, student, for this one? So the image will form somewhere up here. Okay, the image will form somewhere up here. So at the same side with the object. So we call it as virtual. Okay, and somehow it is upright. Okay, why upright? Because object above principal axis, image also above principal axis, and the size has been magnified. So here is applied in an eyepiece of a telescope. Okay, and the last position, U less than F. So now the object is very close to the lens, where object distance, this is object distance, less than the focal length. Okay, so apply rule number 1, the red line, and then apply rule number 2, the green line. So here the line is diverge, mean they will be intersect at the opposite side. Okay, these two lines will be intersect at the opposite side. So here is where our image form at. So it form at the same side with the object. So we call it as virtual. Okay, and it is upright, and the size you can see, image is larger compared to the object. So the image is said to be magnified. So where do we apply this? When we are using magnifying glass. Okay, did you notice when you use magnifying glass, the object is placed very close to the lens. So object distance less than F, and you will see the image is magnified for a few times compared to the actual object. Okay, so are you clear with this, student? How to determine characteristic of image depend on the object, position of object. If you can understand this or can follow me, please type yes in the in-call messages. May I see some response? If you are clear how to apply, how to draw the ray diagram by applying the 3 rules in order to determine characteristic of image formed by convex lens. Okay, if you can follow me, please type yes in the in-call messages. Okay, see who's following me. Okay, so far we have 35 participants, 35 including me. Okay, Jingshun, can you follow? Xin Yu, Xin Yan, Junbin, William, Xiang Jie, Se Yong. Are you doing good there? Jin Yang, Rui Yang, Hok Yen. Okay, anybody would like to ask any question? Okay, if you don't have, I think we continue with the next slide. Okay, students, so that goes for convex lens. Okay, now let's take a look at concave lens. Okay, so for concave lens, it's very easy because the image position and characteristic of image form is now not depend. Okay, it is not depending on the position of the object. Why? Okay, if you look at this GIF, see, when we change the position of object, you can see the image will always form somewhere at this position. Okay, always form at this position, less than the focal length in front of the concave lens. Okay, so in conclusion, we can say the characteristic and image position formed by concave lens is always formed at the same side at the object. Mean it doesn't matter where we place the object at, the characteristic of image is always, number 1, always virtual. See? Second, always upright. Okay, and then third, always diminish, means smaller than the object. Okay, as you can see from the GIF here. So this is how we draw light ray parallel to the principal axis diverge out. Okay, after passing through concave lens. So remember the 3 characteristics for concave, VUD. Okay, VUD, wood. Virtual, upright, diminish. 1 characteristic only. Always virtual, upright, and diminish regardless of their position of object. Okay, so that goes for concave. For convex, it depends on 6 different positions where we place the object at. Alright, okay. So this is example. Okay, the example of drawing a ray diagram for concave lens. Okay, we took the first drawing. Now we place the object beyond 2F, greater than 2F. So this is the object, the green color. So we apply rule number 1, the yellow light ray. So a light ray passing through the optical center, so not refracted, continue travel in a straight line. Okay, then second, we apply the second rule. Okay, a light ray parallel to the principal axis and then diverge. Remember, it must be diverged out from the focal point in front. So this is the intersecting point. Okay, so where our image form at. Okay, so the image is virtual, upright, and diminished. Okay, virtual, upright, and diminished. Why virtual? Form at the same side with the object in front of the lens. Upright, object above principal axis, image also above principal axis. And then the size is less, smaller compared to the object. So we call it as diminished. Okay, this one also the same. Now we place the object less than the focal length. So this is our object, less than the focal length. Okay, so we apply rule number 1, the yellow light ray. Second rule, okay, rule number 2, the pink light ray. Again, this is the intersecting point between these two light ray. So our image also virtual, upright, and diminished. Okay, so what is the purpose of concave lens? It is used to correct short-sightedness, okay, especially for young people, okay, students. Okay, then. Okay, so this is the third activity. Okay, to determine position and characteristic of image formed by convex lens. So now we understand the rules of drawing in order to determine characteristic of image. So this is the second method to determine the characteristic by conducting an experiment using the optical apparatus. Okay, so this is the diagram of apparatus. We need a convex lens placed in a lens holder, and this is our light ray sources, and this is our widescreen. Okay, so we place a transparent paper with an arrow drawing there as our object. Okay, so what we need to do, we adjust the position of the convex lens until you can see a sharp image of arrow form here in this widescreen. All right. Okay, so here we use a convex lens with the focal length of 10 centimeter and also a concave lens with the focal length of negative 10 centimeter. So when you go and buy at the store, you can check the specification. Okay, this lens has how much power or what is the focal length of this lens. It is all written in the specification for each unit. Okay, okay, then okay, this is the direction given. So we begin by place the object distance at 30 centimeter. Okay, if we go back to the diagram, so first we place this ray box at a distance 30 centimeter from the lens holder. Okay, and then we observe the image produced. We adjust the widescreen until we can it can cast a sharp image on the screen. Then we measure what is the image distance, and then we repeat the experiment with object distance 20, 15, and 8. So you will adjust the widescreen until can form a sharp image. So finally we measure the image distance V. Okay, and students, it goes the same for concave lens. Okay, so let's say this is the tabulation of data determined from this activity. Okay, first we have 4 different position of object. Okay, this is for convex lens. First, we place beyond 2F, 30 centimeter, and then at F, which is 20 centimeter between F and 2F, and then this one between F and the optical center, 8 centimeter. Okay, and this is the image distance measured. Okay, distance from the convex lens to the widescreen. Let's say this one 15 cm, this one 20 cm, and this is 30 cm, and this give negative 40 cm. Later I'll tell you why negative there, why there's negative sign there. Okay. Okay, then this is the characteristic of image determined. Okay, beyond 2F, so you can compare with the ray diagram just now. It will be real, inverted, diminished. At 2F, real, inverted, and same size. If here, it is real, inverted, and magnified. Okay, and then less than F, it will be virtual, upright, and magnified. Okay. So students, when we look at this, actually you can come to a conclusion. Okay, what is the conclusion we can make here? When the object distance u, okay, object distance u greater than f. Okay, mean when the object distance greater than f, then the image produced will be real and inverted. Okay, the pair for real is inverted. Okay, all real image must be inverted. So this is the conclusion. When u greater than f, the image must be real and inverted. Okay, and then later when u equal to f. So when u equal to f, what happened? The object is virtual and upright. Okay, and then later when u less than f, when u less than f, so what happened? The image is virtual and upright. Okay, so this is the conclusion. The size later you can compare. Okay, you can compare. Okay, so for concave lens. Okay, so this is the 3 different position. So first we place the object at the distance of 20 centimeter, okay, from the lens. So this is the distance of image produced. And this one we place the object at the distance 15 cm. This is the distance of image produced. And then we place the object less than f. Okay, and this is the distance of image produced. Okay. So in all 3 positions, it will form the same characteristic of image. Virtual, upright, and diminished. Okay, where the position of image always less than f, as shown here in this GIF. Okay, so for concave lens, remember, any position you place the object at, characteristic of image always virtual, upright, and diminished. Okay, the negative sign for V here showing that the image produced is virtual. Okay, virtual means we cannot see the image at the screen. Tak boleh nampak daripada screen. Okay, the image does not appear at the screen. Okay, real image, we can see the image appear on the screen. So that is the difference between real and virtual image. Okay, and this is the discussion or 3 questions that may come out from this activity. Okay, so first, a real image, okay, for convex lens form when the object is placed at greater distance than f. So remember, when u greater than f, real image is formed. Okay. Meanwhile, when u is equal or less than f, it will form virtual image. Okay. For concave, okay, second question, what are common characteristics for real image? As I mentioned just now, all real image formed by convex lens are inverted. Okay, students, so the pair is real pair with inverted. Okay, virtual image pair with upright. Okay, so if you write the conclusion, we can form a Vuri, V-U-R-I, Vuri, virtual, upright, real, inverted. Okay, the pair. Virtual pair with upright, real image pair with inverted. There is no such real and upright, you takkan jumpa. And there is no such virtual and inverted. Okay, you may not found them. Or lenses. The pair is virtual pairing with upright, real pair with inverted. Okay, and this one for concave lens, always upright, always virtual, always diminish. Okay, independent on the object distance. Okay, so let us try to do first some exercises. If you can follow me, I think there will be no problem for you to answer this. Okay, let us try question 1, students. Objective question. We have a student draw light ray passing through lens P, Q, R, and S. Show in this diagram. F is the focal point for all these lenses. So this is lens P. Number 1, we have lens P. Number 2, we have lens Q. Number 3, we have lens R. And then number 4, we have lens S. Okay. Can you tell me which drawing is correct, showing the path of the light ray? Okay, anyone, you may share your answer. Is it A, 2 only? Or is it B, 1 and 3? Is it C, 1, 2, and 4? Or is it D, 1, 2, 3, and 4? So we can check one by one. Okay, look at the first one. Correct or not? Now the light ray travel exactly at the principal axis. So what happened? It will continue travel in a straight line. No refraction. So this one, correct. Number 1 is correct. Okay, how about number 2? Okay, number 2, we have concave lens. Remember, concave lens is a diverging lens. So a light ray travel parallel to the principal axis. So what happened? It will be diverged out from the focal point at the front. So this is also correct. Okay, number 3, correct or not? Now we have convex lens. Okay, convex lens. A light ray parallel to the principal axis. So after passing through, it should be converged at where? Supposed to be converge at the focal point here. Converge at F. But now it does not converge at F. So this is wrong. Number 3 is wrong. Okay, number 4. Now we have convex lens where light ray is travel through the optical center. Remember, when travel through the optical center, it will continue travel in a straight line. Okay, let's say here we have another light travel through the optical center, so continue travel in a straight line. So this one correct. So the one that correct is number 1, number 2, and number 4. So our answer should be C. 1, 2, and 4. Okay. Okay, then check. Okay, C, yes, very good. Ruyang says C. Okay, thank you for your response. Okay, then the second question. Okay, now the question is, where should an object be placed in front of a convex lens with focal length F so that it can act as a magnifying glass? Okay, so magnifying glass, which one? Where we should place the object? Is it less than F, between F and 2F, or equal to F, equal to 2F, or more than 2F? So this one, where to look? We can refer to this table just now. Okay. Can you find where is magnifying glass? Okay, so here, magnifying glass. So where we should place the object? U less than F. Okay, U less than F. So when we go back to this question, so where should we place our object at? Less than F. Okay, U less than F. Then only the convex lens will act as a magnifying glass. Alright, okay, now third question. Diagram 22 shows an object O. This is our object placed at 2F. Okay, at the distance of 2F of a concave lens. You can highlight concave lens. Okay, the question is, at which point the position of image form? Okay, so to know this one, you have to draw the ray diagram. Okay, we try to draw the ray diagram. So what happened? You can apply the first rule. The first rule, remember, we draw a straight line to the optical center. So continue travel in straight line. Sorry, my line is shaggy because I am using freehand here. Okay, no ruler. Okay, then second rule, Okay, how to draw the second rule? From the object, we draw a light ray parallel to the principal axis. Okay, remember this is concave. So what happened? It will be diverge out, diverge. Okay, from the focal point. Okay, diverge here. So this is where our image form at. So our image form somewhere here at point B. Okay, so answer for question 3, image form at B, point B. Okay, in front of the lenses at the distance less than the focal length. Alright? Okay, then, okay, this is question number 4. You are given two diagram 4.1, 4.2 of two different distances in front of convex lens. So you have to study this diagram. So the first object is placed here. Okay, so this is our object distance. So now U is greater than 2F. Okay, for this one, this is our object position. U is between F and 2F. Okay, U is placed between F and 2F. Okay, so F less than U, then less than 2F. So this is the E position of object. Okay, and this is where the image form at for the second diagram, and this is where the image form at, okay, for the first diagram. Okay, so the first question they ask you, state two common characteristic of the image formed in 4.1 and 4.2. Okay, can you name two same characteristic here, student, in 4.1 and 4.2? Okay, there are two common characteristic. The first one, the position, right, both form at the opposite side, okay, of the object. So we call them as real or virtual, student. 4.1. Is the image real or virtual? Okay, so we call the object, we call the image as real image. Okay, so we call them as real. And somehow both are inverted. Object above, this one object above, image below principal axis. So the same characteristic, real and inverted. Can we say the size? The size you cannot say common because this one, the size is diminished. Okay, for this one, the size has been magnified. So they are not the same. Okay, so the two common characteristics, both are real and both are inverted. Okay, then compare the object distance. So how we do comparison? Remember, compare the object distance. So we can say object distance in 4.1 greater than that in diagram 4.2. Okay, then compare image distance. So you can compare the image distance. Image distance in 4.1 is less than in diagram 4.2. Just check from the drawing. Compare the size. So which one bigger? 4.2 has a greater size. So we can say size of image in diagram 4.1 less than that in diagram 4.2 or vice versa. Okay, then based on your answer, state the relationship between object distance and image distance. So what happened when object distance increases, image distance decreases. Okay, or vice versa. Vice versa means you can write when object distance decreases, so image distance increases. Okay, then state relationship between object distance and size of image. So you can see from the diagram, object distance increases, size of image decreases, or vice versa. Alright, okay. So for this one, I am not recommend you to write directly and inversely proportional because it is not a safe answer every time. Sometimes it is accepted and there is a year it will be rejected. So it is better if you write in this form, okay? Object distance increases, image distance decreases. Object distance increases, size of image decreases. Okay? Okay, please be aware with that. Okay, now this is application. This diagram shows magnifying glass with the sunlight, okay, passing through it. A piece of paper is put under the magnifying glass. Okay, so we place a paper down here. So the first question, where, student, where should we place the paper to obtain the strongest heat from the sun? So where to place the paper at? Is it placed less than F, placed at F, in between F and 2F, or at 2F or beyond 2F? So where we place the paper? So remember, this is magnifying glass. It apply convex lens. So where do you think is the best position to place? So we place the paper at the focal point of the magnifying glass. Okay, why must place there? Because this is the point where all parallel light from the sun will be focused at after passing through this magnifying glass. Okay. Okay, so this question used to come out in past year SPM, but I don't remember which year. They use in a kettle, okay, to boil a water inside a kettle using a parabolic, using lenses of parabolic. So we should place the kettle at the focal point of the device given, right? Okay, then this is the another example of SPM past year question. Okay, now they ask you to draw a ray diagram. First, name the lens in this diagram. Okay, student, can you tell me this lens? Is this convex or concave lens, students? It is thinner at the center, so it should be, yes, it should be concave lens. Okay. Second, we have to sketch a ray diagram to show the formation of image. So this is our object. Okay, our object. So you can apply the first rule, draw a ray diagram from the object to the optical center, continue travel in straight line. Okay, then we can apply the second rule. Okay, second rule, a light ray parallel to the principal axis and then diverge out from the focal point in front. So this is the intersection between the two light ray where our image form at. Okay. So you draw the image and then label it with I or right there, image. Okay, so 3 marks for that. And then this is the characteristic for image form. Remember, for concave lens, the image is always virtual, upright, diminished. Okay, just put this in mind. Okay, independent on the object distance, the image is always virtual, upright, and diminished for concave lenses. Okay. So far, we have discussed 3 learning standard and this will be the last one, 6.3.4, to explain linear magnification. Okay, linear magnification. Okay, before that, you can you go and take your workbook, turn to page 134. Okay, please come and get your workbook and turn to page 134. Okay, 134. 6.3, image formation by lenses. Okay, I want you to complete the ray diagram for both convex and concave lenses in this page, page 134. Activity number 1A. Okay, activity. So you can see there are 1, 2, 3, 4, 5 parallel light ray directed to both concave and convex lenses. So what happened to all these 5 rays after passing through the lenses? So you need to draw the ray diagram. Second, to mark the focal point with F, and then mark the optical center with O, and then finally mark the focal length. Can you make a correction there? Focal length with symbol small f. So I read the instruction and you please do some small correction there. Okay, question 1A in page 134. Draw the ray diagrams when the parallel light passes through a convex lens and a concave lens. Mark the focal point F, center of lens O, and focal length, student, not focal point. Okay, the final terms itu focal length, okay, with small f. Okay, so you do both for convex and concave lenses. So for convex, it should be converge to the focal point behind. Okay, and for concave, it should be diverge from the focal point at the front. Okay, got it? Dapat Okay. Okay, so you can take your time and complete the drawing later. 1A, complete the drawing for 1A for convex and concave. Okay, then yeah, I want you to complete B as well. What happened to the parallel light ray after passing through the convex lens and then concave lens? Okay, and then number 2, later you can complete the definition for the following terms. Started with focal point, ended with optical center at page 135. Yeah, so this is your homework for today. Complete number 1, A, B, and then number 2. Later, you can refer to my PowerPoint slide, which I share to you in the Telegram group. Okay, so now let us go to this linear magnification, the final learning standard 6.3.4. Okay, student, talking about magnification. So we understand the word magnification from the word magnify. Mean the image will be magnified, bigger compared to the object. So as you can see written here, when an object is observed through magnifying glass at a distance less than the focal length, so the image formed is magnified. Okay, so the comparison between size of image and size of object can be expressed in terms of ratio, okay, of the height of image to the height of object. So we call this ratio as linear magnification. So what is linear magnification, students? Linear magnification is the ratio. Okay, it's the ratio of height of image to the height of object. Very simple. If they ask you, state the meaning of linear magnification. So answer, the ratio of the height of image to the height of object. Hi to ho, the formula. M equal to hi divide ho. Okay. Okay, for example, show in this diagram. We place convex lens there. Object is placed in between F and 2F. And according to this ray diagram, this is where the image formed at. So we have HO, this is the height of object, and this is HI, the height of image. So we want to know how many times this image has been magnified, okay, compared to the object. So we can apply this formula. M equal HI divide HO. Okay. And students, this is the second ratio we can use. So based on the figure, the ratio of height of the image to the height of object is the same as the ratio of image distance to the object distance. So this is the second formula. Linear magnification also defined as ratio of image distance V to object distance U. So either you use the first formula, M equal to HI divide HO, or if not given the height, you can use the second formula. Magnification is also determined from image distance divide object distance. Okay, and later when you find the answer for M, if you find that the value for M is less than 1, so what does it mean? It means our image is diminished, means smaller than the object. If later you find M exactly equal to 1, mean we have object and image of equal or same size. Okay, and when you do the calculation, you find M, value of M greater than 1. So we understand our image is greater than the object, or we say the image has been magnified. Okay, remember, very simple. M less than 1, image diminish. M equal to 1, image same size as object. M greater than 1, image is magnified. Okay. Okay, for example here, okay, let's say, okay, I think you jot down the formula for M equal to H1 divide HO. Second, M equal to V divide U. Okay, so let's try, let's apply in this question. Object with a height 5 centimeter placed 20 cm from convex lens. A sharp image is formed on the screen 40 centimeter from the convex lens. So the question is, what is the height of the image? Okay, so first, you are given 5 centimeters. So what is 5 centimeter? Object with the height. So this is HO, 5 centimeter. And then 20 centimeter, this is U, object distance. Okay. And then sharp image form 40 centimeter from the, so 40 cm is V, image distance. So we are looking for HI, height of image. So what is the relationship between U, V, HI, and HO? Okay, they are related from this formula. Okay, HI divide HO equal to V divide U. Okay, this is a magnification formula, linear magnification. So we just do the substitution. Okay, HI, okay, divide 5, object height 40 cm, image distance 20 cm, object distance. So from this, we determine the height of image is 10 centimeter. So answer donkey. Okay, so same question, you are given a diagram, show formation of image by convex lens. So this is where we place the object at. The height is 2 centimeter. And the object distance is given 8 centimeter. Okay, height of image we are looking for. They don't give V directly, but you are given with this information. The distance from the object to the image is 26. So we know object distance is 8. So we can find image distance be height. Okay, by minus 26 minus 8. Okay, which means image distance is 18 centimeter. 26 minus 8. So give you back here 18 centimeter. So this is the information given. So again, we can find height of image by applying this formula. Okay, so this is a substitution. So you will find image height is 4.5 centimeter. Okay, so this is the two question involving linear magnification. Okay, so this is an additional notes. It does not include in your textbook power of lens. Okay, for those who are wearing lenses, you know what is the power of your lens, and it is somehow different from the left side and the right side. Okay, and the power of lenses ini determine the thickness of our lens and the length of the focal length, okay, of the lenses. Okay, we check first, student, what is meant by power of lens. Power of lens refers to the ability of the lens to bend or to refract light rays entering it. And power is measured in the unit of diopter. So if you compare here, we have both are convex lens, but they are different in thickness. Okay. On the left side, we have a thinner convex lens. And here we have a thicker convex lens. Okay, if you look at angle theta 1 here, what is angle theta? Angle theta ini is the angle of deviation. Means how much the light have been refracted. So you can see here, theta 2 is greater, okay, compared to theta 1. So we understand thicker convex lenses converge light at a bigger angle, which means it has a higher power compared to thinner convex lens. Okay, so remember, a thicker convex lens has a higher power compared to thinner convex lens. Okay, because it bend more light, it able to bend more light which pass through, it able to refract more light at the greater angle that passing through it. Okay, and this one, the thickness of convex lens. Sama lah ni, continuation from the previous one. So we understand when the thickness is greater for convex lens, the power also greater. Okay, the thicker the center, the shorter its focal length, and then the higher the power of the lens is. So from here, we have two information. Number one, when the lens is thicker, the power is higher. Okay. Second, you can see when the power is higher, the focal length will be shorter. Okay, which means thicker lenses has the shorter focal length. Okay, and this is the formula, relate power and focal length. So power is inversely proportional to focal length. When power increases, focal length decreases. So how to find power? Power is equal to 1 over F. F here is in meter, the focal length. Okay, power is 1 over F. F is measured in a unit of meter. Okay, and this one for concave lens. How to determine power of concave lens? Which concave lens has a greater power, a thin one or a thick one? So from this you can see the angle theta is greater for thinner concave lens. Means for concave lens, thinner lens has a higher power. Okay, and focal length shorter. Right, shorter focal length. Higher power, shorter focal length for thinner concave lens. Okay. Okay, this is the application. Okay, problem solving involving power of lens. Kita tengok dua contoh. Okay, given here number one, focal length of a convex lens is 20 cm. Okay, so find the power of the lens. So this is a very direct question. Okay, so this is the formula. Power is 1 over F. 20 cm, remember, must be converted into meter. So 20 cm is 0.2. Why positive there? Remember, for convex lens, the focal length is taken as positive. Okay, sebab dia real focal length. So it is taken as positive. So the power also will be positive. 5 diopter, the unit. Okay. While for second question, we are now given with concave lens. Okay, given the focal length is 10 centimeter. Again, find the power of the lens. Okay, so students, for concave lens, this is the formula. P equal 1 over F. F must be in meter. So for focal length, this is the focal length. The focal length is called as virtual focal length. So it is considered as negative. Okay, the length considered as negative. So negative 0.1. So the power for concave lens also negative. Okay, negative 10 diopter. Okay, so positive for convex, negative for concave. Alright. Okay. Okay, this is the next question. Okay, you are given diagram 11.1, 11.2 show parallel light. So we have 3 parallel light ray here. This one also 3 parallel light ray. Okay, we have lens X. Here is lens Y. Both are convex lens, but they are different in thickness, as you can see. Okay, so here, this is the focal length, 5 cm shorter. Here, this is the focal length, 20 centimeter longer. Okay, so first, what is meant by focal length, student? So this one you can refer back to the table of optical term I show you just now. So this is question taken from trial SBP 2023. Okay, so this is the definition. Focal length is a distance between focal point and optical center. Right? Okay. And this one, you have to observe diagram 11.1 and 11.2 and then to compare the thickness. So first we compare the thickness. So remember, this is essay question. Okay, essay question. So we must write the parameter. Don't just mention diagram 11.1 greater than diagram 11. You will lose marks somewhere. So compare the thickness. So we say thickness of lens in diagram 11.1 greater. Okay, then in 11.2. Second, compare the angle theta. Okay, angle theta you can show from the diagram. Angle theta in 11.1 greater than that in 11.2. Then third, compare the focal length. So focal length, you can see focal length in diagram 11.1 less than in diagram 11.2. If you notice, I always place 11.1 in front. Okay, so later easy for me to write the relationship. You can put 11.2 in front as well, no problem. Okay, and fourth, deduce the relationship between thickness of lens, angle theta, and focal length. So you have write two relationship here. First, relate the thickness to the angle. Second, relate the thickness to the focal length. Okay, I repeat. First, you relate thickness to the angle. Second, relate thickness to the focal length. So for number 4, the thickness of the lens increases. So what happened? Angle theta increases. Okay, second, thickness of lens increases. So focal length decreases. So this is the relationship. And finally, name the physics phenomenon involved. Okay, for the 5th mark. So what physics phenomenon involved in lens? So the phenomenon is refraction of light. Okay, so 5 mark. This is how we tackle this kind of question in paper 2, section C, question 11 on comparing and deduce relationship and to name physics phenomenon involved. Okay. And then this is question C. You are given diagram 11.3. It shows a tool which consists of lens cube that used by gem cutter to examine small gems. Okay, so the question is explain how lens cube can be used as a magnifying glass. So 4 marks. How cube can act as a magnifying glass. So you can use the WH question here. First, what kind of lens can you use to make magnifying glass? So first, we must use convex lens. Okay, the first mark. And then where to place the object. So it becomes a magnifying glass. Okay, so the object must be placed at the distance shorter than the focal length. Or you can write U must be less than F. Okay, and then what happened? You can tell how the process occur. Okay, light ray from the object, which is parallel to the principal axis, refracted to the focal point after passing through the lens. So actually, this is the second rule of drawing the ray diagram. Okay, and then light ray from the object propagate to the optical center is not refracted or continue travel in straight line. So this is the first rule of drawing the ray diagram. Okay, and finally, the image is formed at the intersection point of these two light rays. So you can get 5 marks from here, but maximum is 4 marks. Okay, okay, students. And then this is the last question for today, long essay, 10 question, application. Okay, application on lenses. So we have diagram 11.4, show a basic structure of a smartphone camera. But the problem here, the image produced is blurry, not clear. Okay, it produced a blur image. So you are required to modify this smartphone camera so the lens will be durable, not easily damaged, and can produce clearer image. Okay, so for this one, you have to remember in your reason, you cannot write durable, not easily damaged, or clearer image. Okay, must give a reason, any reason other than this. Okay, same meaning but different sentence. Okay, describe, explain the modification you can make to the lens characteristic, including its focal length, optical density, the aperture size, and any supplementary tool or features you can add or the camera aperture. So 10 marks. So this one is an open-ended essay. No limit. You can give as much point as you can. Boleh bagi beberapa modification, more than 5. You can give more than 5 but not less than that. Okay, so first you can talk about the focal length. So we are using longer focal length. So longer focal length will give you bigger magnification, or it will give you thinner, thinner, thinner lens. So the phone will be thinner. Okay. Second, we can use high optical density of lens. So high optical density lens will refract more light. Okay. And also you can write the reason, longer focal length. So the smartphone will be thinner. Okay. Then student, the size of the camera aperture, the opening should be big. So more light can enter the camera. Okay, more light enter, more light reflect. So which means the image form will be brighter. Okay, brighter image will be produced. And then the next modification, we can add some transparent lens cover. Okay, we can add transparent lens cover in front of the camera. So this is to prevent dust or scratches on the lens surface. And last but not least, we can use a low rate of oxidation of lens so that our lenses will be long lasting, okay, or prevent it to be blurred, okay, in a shorter time. Okay, so this is modification and reason recommended for this question. Okay, in order to overcome the blur image produced by the initial lenses on the smartphone camera. Okay. Okay, so I guess that's all for today. Image formation